Sangil, for the nice introduction. Also, I have to say I have very good memories for the year we spent together at Georgia Tech when we were both postdocs of Robin Thomas. And I hope I will be able to come as often in future as I was coming in the last year. And I hope you will also visit Warwick at some point. Okay, so thank you for the introduction, thank you for the invitation, and thank you for the opportunity to give me this talk here. And I have to admit I'm not that much used to using microphones, so in case there's some problems with hearing me, or you can't hear me, or there's any problem with the audio system, please let me know. So today I want to be talking about permutations. The first part of the talk and the most of the talk will be concerned with quasi-random permutation, which is a joint work with Oleg Pikhurko, who moved to Warwick from CMU about a year ago. And the second part of the talk will be more computer science oriented, and it's a joint work with a graduate student of mine, Tereza Klimoshova. So the first question is what I mean by a permutation. So we may view permutations from the more algebraic point of view or more combinatorial point of view. So for me, permutation will be just a sequence of n numbers from 1 to n with a fixed order. So I gave some examples of permutation of order 5 on the slide. And of course, since I promised to be talking about quasi-random permutation, and the question you might ask, and probably I should answer, is what does it mean when a permutation is random? And of course, whenever I fix one permutation, it's never random, because when it's fixed and I fix a permutation, it definitely has properties that most of the permutations don't have. So I will not define really a notion of randomness or quasi-randomness for one permutation, and instead of that I will be considering sequences of permutations of increasing orders. And I would call a sequence of permutation quasi-random if this sequence in the limit has all the properties, or at least most of the properties, that a random permutation would have asymptotically almost surely. So by a random permutation, I mean when you choose randomly, uniformly, one of the n factorial permutations of order n, and I will say that a permutation has property asymptotically almost surely if the probability that a random permutation of order n has that property is 1 in the limit. So it grows to 1 as n goes to infinity. So one example of a property, of such a property is, for instance, the density of subpermutations. So if I take a random permutation and I look at pairs of numbers such that, let's say pairs of indices I and j, such that the ith element is smaller than the jth element, I should see roughly half of them. So this is one of the properties that the random permutation has asymptotically almost surely, and probably I would like to say that a sequence of permutations, if it should be pseudo-random, then this should be one of the properties it should have. So let me now be a little bit more precise what I mean by a subpermutation. So if I am given a permutation, so I have chosen this permutation of order 6 as an example, then a subpermutation is I choose some particular positions in the permutation, maybe the one that are displayed in the red, and then I just read these numbers in the order. So 3 is the smallest, so therefore 1 comes here, 5 is the second smallest, therefore I get 2 here, and 6 is the largest, therefore I get 3. So if I have a small permutation sigma, and I have a big permutation capital pi, then I will be using d sigma pi for the density of sigma in pi. So what I mean by that is that I randomly choose positions in pi. The number of positions I'm going to choose is equal to the order of sigma, and the density of sigma is just the probability that the subpermutation that I'm going to see will be sigma. And now I will say that a sequence of permutation has property pk if the probability that I see a permutation, that I see any permutation of order k, the limit of this density is 1 over k factorial. So I see all the permutations of order k with the same probability. And of course, if I have a random permutation, then it has property pk with probability 1 asymptotically almost surely. So it has property pk asymptotically almost surely. So this is definitely a good set of properties that I would like my pseudo-randomness to have. And Graham asked whether actually I need to check this for all values k, or there could be probably when there is some small integer k0, such that if I know that the sequence of permutations has property pk0, then it would have property pk for all k which are at least k0. And the main result I'm going to present today is actually a positive answer to this question, and namely with Oleg Pigurkov we prove that the right number is k is 4 and it cannot be decreased to 3. So in other words, if I have a sequence of permutation and I see, and in the limit the density of any of the 24 permutations of order 4 viewed as subpermutation with 1 over 24, then the density of any permutation of arbitrary order, let's say order L, in the limit is 1 over L factorial. And you cannot decrease, is there a question? No. You cannot decrease this 4 to 3, and I will show you an example of that. And I have to say that this notion of quasi-randomness in the stronger sense that the sequence has property pk for all k was studied by Cooper, and he in fact provided a whole list of properties that are actually equivalent to this. So before I continue with or I present our approach and the proof of this theorem, let me say something about quasi-randomness of graphs, which is probably a topic which is more studied and somewhat better understood. So of course one may ask, what does it mean? What is a random graph? There are several models, and the model that I will be talking on this slide is the classical G(n)1/2 model. So a random graph is a graph on vertices and vertices where I include every edge with probability 1/2 independently of the other edges. And there's a paper by Chang, Graham and Wilson from 1989, and what they showed is that actually the property of there were many properties that a random graph, G(n)1/2 graph, asymptotically almost surely has, and if you have a sequence of graphs and the graphs in your sequence has one of these properties, they have all the others. So one of the properties was that all the densities of all the subgraphs are as is in G(n)1/2. So you may view this as an analog of the densities of all subpermutations. And this is actually equivalent, that you don't have to look at the densities of all subgraphs. It's just enough to have the right density of edges and the right density of C4s. So if you have a sequence of graphs where the ratio of the number of edges in the limit is half, and the density or the probability if you pick 4 vertices that would you see that you find a 4 cycle on them is as in G(n)1/2, then if you take any graph, being it a triangle K5 or any bigger graph, where the density in your sequence will be the same as in G(n)1/2. So this is, in some sense, it's an analog to what we're doing. But our proof is completely different, and it's not inspired by this proof. And this is actually equivalent to having a certain separation between the two largest eigenvalues for the adjacency matrix or being dense in everywhere in some sense, and many other properties. And also this phenomenon was studied in other contexts, for example for hypergraphs, or I want to point out in particular this paper, this recent paper by Lenz and Mubai, where they studied the analog of the eigenvalues, or this characterization through eigenvalues for hypergraphs, and they actually obtained kind of a hierarchy of different notions of quasi-randomness. And it's a very nice paper, and I think it's already appeared on arXiv. So quasi-randomness also appears in some other areas, and in particular the famous Semeredi regularity lemma says that every graph can be partitioned into a bounded number of paths that mutually interact in a pseudo-random way. where of course we have to say what do you mean by pseudo-random, and I don't want to go into technical details right now, but I just want to mention that you may use the semi-ready regularity lemma to derive some theorems from number theory, like Roth's theorem, which says that in any dense subsets of integers you have an arithmetic progression of length 3, or its generalization, which is semi-ready theorem asserting that you can find arbitrary long arithmetic sequences in dense subsets of integers. And the regularity lemma also is applied in computer science in the area called property testing, that I will be talking more in the second half of the talk. And essentially in the area of property testing, you're given a large input and you want to design an algorithm that will not read the whole input but just a part of it, and based on the sample it reads, it will be able to make some conclusions about the properties of your input. And I will make this more precise in the second half of the talk. So let me go now back to quasi-random permutations, and let me say that a sequence of permutations is convergent if there exists a subsequence, if the densities of all the permutations sub-permutations in that sequence converges. So once more, so if I'm given a sequence of permutation, then for that sequence I can define a sequence of densities for every permutation sigma, and I want this quantity to have a limit for every choice of sigma. So of course if I have a sequence of permutation, I can choose a subsequence that is convergent in this sense, and that's basically a standard argument. So what I'm going to do is I'm going to study the properties of the lead object associated with convergent sequences of permutations. So this is a well-developed theory for graphs, so-called graph limits, which was among others studied by Levas and Szegedi, and it has many applications in particular in extremal combinatorics, where it's used for the notion of flag algebras, which was formally developed by Rasborov. So here I will be looking at the limit object of a convergent sequence permutations, which I'm going to introduce on the next slide, and the theory associated with these objects was developed in a similar way as the theory for graphs by Hopenko, Hayakawa, Moreira, and Sampaio. And it's very, very analogous to the already existing theory of graph limits. So suppose, so first of all, let me recall what a graph limit is. So for a sequence of graphs, the graph limit is a measurable function on a unit square to 0, 1. And you may kind of think of this as an analog or kind of a continuous analog of an adjacency matrix. So for permutations, and I have to say, before I said I'm going to use the theory developed by Kohayakawa and his co-authors, but I'm going to write with a slightly different limit object than they do, but they're kind of identical in the sense that there's an easy transformation between the two. So for the permutations, the limit object will be a measure on a unit square which satisfies something that I call unit marginus, and essentially what I want is that any rectangle going from top to bottom has measure equal to its width, and any rectangle going from left to right has measure equal to its height. So this is written here. So any rectangle going from top to bottom or from left to right, they have measures equal to either their width or their height. So, and how I do define the measure for a sequence of permutations. So for example, so what I do is I define a measure for every permutation, and I define it in a naive way. So for example, if I have a permutation 1, 2, 3, 4, 5, then I will divide unit square into 5 times 5 grid and put all the mass in these squares, which corresponds to 1 because 1 is on the first coordinate, 2 because it's on the second coordinate, 3 because it's on the third coordinate, 4 because it's on the fourth coordinate, and 5 because it's on the fifth coordinate. And if I have a sequence of permutations which are all of the form 1 to k, just increasing, so 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, 4, 5, 1, 2, 3, 4, 6, and so on, when I will define a sequence of measures, and this measure in the weak sense converges to a measure that's fully concentrated along this diagonal. And I will call this measure to be the limit of that convergent sequence of permutations. Similarly, if I have permutations that are formed by kind of two increasing parts, where maybe first I have all the odd numbers, and when I have all the even numbers sorted from the lowest to the largest, then the limit will be a measure that's fully concentrated along these two lines. So I just show you that if you give me, so I didn't show all the technical details, but to kind of have to trust me, that if you're given a convergent sequence of permutations, the convergence means that the densities do converge for every choice of the permutation you're looking at. So if you're given a convergent sequence of permutation, when this limit exists, and in the sense that the associated measures with the individual permutations appearing in the sequence, there's a limit, there's a unique limit on the unit square to which these measures do converge. On the other hand, if I give you a measure on the unit square, I may sample the permutations, I may actually sample the whole sequence of permutations that would resemble the original sequence. So if I have a measure, this will be a probability measure, I may just sample random points. So in this case, I will just sample, if I want to sample a permutation of length 5, then I will, of course, always get a permutation which is 1, 2, 3, 4, 5. Because I will just sample 5 points and they must lie on this diagonal. In this case, maybe I will get 3 points and 2 points maybe on this line, or 1 point here or 4 points here. But the nice thing is that as I keep sampling, so I may maybe construct a sequence of permutation where first I sample a permutation of order 2, then of order 3, 4, and so on. When with probability 1, the sequence that I have sampled is convergent, and its limit is the measure I have started with. So I have a correspondence between, I can go from a convergent sequence of permutations to the limit object, which is this measure with the unit marginals, and once I have this limit object, I can sample from it permutations of arbitrary large order. With probability 1, the sequence of permutations I will sample will be convergent, and the measure I started with will be actually the limit of that sequence. So to get used to this notion, let me show you a counterexample for P3. So by counterexample for P3, I mean I want to show you a sequence of permutations such that the density of every 3-element permutation in that sequence is 1 over 6, which is 1 over 3 factorial. But this sequence is not quasi-random in the sense that the density of any permutation would converge to 1 over its order factorial. So I will start with two limits. I will start with this limit and this limit. So this is a measure fully concentrated along these 4 segments, and this is a limit fully concentrated along these 2 diagonals. And you may verify that the probability if I sample a large permutation according to this measure, that the density of 1, 2, 3 is 1 over 8, and the density of 1, 2, 3 if I sample a large permutation according to this measure is 1/4. So now I'm going to convexly combine these 2 measures in the following sense. I will view these 2 diagonals as rectangles which are very, very thin, and I will start opening them. So I will so this will be something that I obtain along the way. So I first will have very, very thin rectangle along the line, and as it opens, I will be getting larger and larger rectangles, and eventually I will get a square which is exactly this one. So I can smoothly transform this measure to this measure just by viewing these 2 lines as very thin rectangles and opening them and moving a smooth transformation when the 2 rectangles become squares and at the point when they start coinciding. So somewhere along this transformation, since the density of 1, 2, 3 is a continuous function as I move from one measure to the other, so somewhere there will be a point where the density is exactly 1 over 6. And now because the measure is symmetric along the vertical and horizontal axis, the density of 3 to 1 is also 1 over 6. And the densities of all the remaining 4 permutations are equal, and there must be quarter of the remaining probability, which is 2/3, but divided by 4, it's again 1/6. So there's a point when if I sample a permutation according to this measure, then the density of any subpermutation of on 3 elements in the sampled permutation will be close to 1 over 6.
Why are the other permutations equal? I didn't understand.
So why are they equal? So 1, 2, 3 and 3, 2, 1, it's easy. And all the remaining ones, if you look at them, they can be obtained by switching along one of the axes. And therefore their densities are equal, and then you get the conclusion. So this is an example that for, and you may find a permutation on 4 vertices that in this picture has density different from 1 over 24. So now let me actually go to proving the claim I mentioned at the beginning, and for that we have to work a little bit more. So recall that I defined a limit object for a convergent sequence of permutation, which was a measure. And of course, if I have a measure, I want to think whether integration with respect to this measure has some combinatorial meaning. So let us start with some simple integrals. So the simplest integral is I maybe integrate just the x-coordinate according to this measure. And I know what I should get, because my measure has unit marginals, so every rectangle going from top to bottom has measure equal to its width. So it's like integrating x according to the uniform measure, and I should get 1/2. But let's try to see whether I can somehow relate this 1/2 to something that's more related to the permutations. So for that, let me make a shortcut that I will be just writing d sigma for the limit of the density of sigma in the sequence. So what does this integration mean? Well, I can also do it, but first I sample a point according to my measure. So this is just based on the integration according to mu. And now I want to find out what its x-coordinate. Well, what's the probability if I sample another point, then it will be in the permutation before it. Because somehow I view the measure as infinitely many points of my permutation. So if I have a point sampled according to the measure mu, and now I want to find out its x-coordinate, then is the probability if I sample another point from my long permutation is before it. Okay, so if I have 2 points and I can have either 1, 2 or 2, 1, I may think this is the first point, and then I want this to be my second point, but what happens with probability 1/2, and the sum of these two densities is 1, and therefore this expression is 1/2 as it should be. So now let us look at a more complex integral, namely x squared, and I can do the same trick. First I sample a point according to the measure mu, and now I know that x-coordinate is a probability that if I sample another point is before it in the permutation. X squared is just a probability that if I sample 2 random points independent of each other, they will be before it in the permutation. And I just have to figure out that if I have so sampling 3 points and I want this to be the point according to the measure, I don't care about the order of these 2 points, so I get 1/3 in front of this expression that sums to 1, so I'm getting 1/3 as I should. So far it seems the field is working nice, but probably these integrals will not bring me too much information. So let us look at a little bit more complex thing. So maybe I want to compute this integral. I want to integrate x and y according to the limit measure mu. So now I sample a point according to the measure mu, and I need to find its x coordinate and y coordinate. Now we already saw what the x coordinate is. It's a probability if I sample another point, it will be before it in the permutation. What is the y coordinate? Y coordinate is the probability if I sample another point, it will be lower than the point I started with. Because the y coordinate tells me the relative height of my point. So now I just look at the densities I look at all the possibilities how 3 points may look like, and then I look what could be the order. So maybe this is my first point, this is my second, this is my third point, or maybe this is my first, this is my second, this is my third point. For each of these triples, I look what will be the probability that if I sample the points in this order, then the first point is to the right from the second point and is larger than the third point. And this will give me some coefficients, and then I find that this integral is actually equal to this expression. And I may also compute another integral. So let me define a function alpha xy to be the measure of the rectangle with the origin at the point 0, 0, which has width x and height y. So I'm just taking, let me draw a picture, and I don't have chalk here. So if this is my unit square, and this is point xy, then alpha xy is the measure of this rectangle. So now what is the integral according to mu of the function alpha xy? Well, I first sample a point, and now what is the measure of this integral? That's the probability if I sample another point, it's before in the permutation, and it's lower than the permutation I sampled first. So I first need to, so the only possibility I get this outcome is that the 2 points I sampled they correspond to subpermutation 1, 2, and 2 is actually the first point to be sampled and 1 is the second one. So this integral is equal to this density. So I just show you that the limit measure actually has a close connection to the densities of subpermutations in the convergent sequence. And now I want to utilize it. And okay, maybe I will need this too. So before I utilize it, let me go a little bit more into the integrals. So we already know we can integrate according to the limit measure. So maybe I want to integrate according to the uniform measure. Might be useful and it will be useful. But the problem is that if I want to integrate according to the uniform measure, I must be able to sample a point inside my unit square uniformly and random. And I will use a trick for that. So if I want to sample a point uniformly and random, when I sample 2 points and I take x coordinate from one of them and y coordinate from the other, I know that my measure has uniform marginals, which means that if I sample one point, its x coordinate is uniformly distributed along the x-axis, and if I sample another point, its y coordinate will be uniformly independently of the first point distributed along the y-axis. So in this way I get a uniform point inside my unit square, and I can express now integrals according to the uniform measure from quantities that I can relate to the 2 points I sampled. So for instance, I can express this integral using densities of 3 elements of permutations, or this integral using densities of 4 elements of permutation, or this integral using densities of 5 elements of permutation. I need 2 points to get a random point according to the uniform measure, and then 3 points to compute this product. So these are some examples of the integrals I may express in terms of densities of the subpermutations in the limit. And now I can show the warm-up for the actual proof, and that's showing that if I have that the property P5 implies Pk for every k. So recall that I want to convince you that if I have a sequence of permutations, such that the density of every 5 elements of permutation is 1 over 5 factorial, then the density of every k elements of permutation is 1 over k factorial. So I'm given a sequence where the densities of 5 elements of permutations are the right one, and maybe it doesn't converge for the densities of some k elements of permutations don't converge, or they converge to a wrong number. So definitely I can choose a subsequence where they converge to a wrong number, and then I can choose a subsequence of this subsequence where all the densities converge, and I have a limit, and the limit is a measure. And now let us look at what I can do. So on the previous slide we saw that I can express this integral in terms of 5 element densities, in terms of densities of 5 elements of permutations, and if the densities of 5 elements of permutations are 1 over 5 factorial each, I can actually compute that this integral is 1 over 9, and I have square here, so it's 1 over 81. And now I will apply Cauchy-Schwarz inequality, and I conclude that this square is at most the product of these two integrals, but this integral again can be expressed actually this can be even expressed in terms of densities of 4 elements of permutations, and this integral is something you can compute because you have just x squared times y squared, and the integration is according to the uniform measure. So this product is 1 over 81. So I have an inequality, but the inequality is tight, and so that means that the left hand side and the right hand side are equal, and therefore this function must be a multiple of this function. So I conclude that the function alpha xy is a multiple of x times y, but alpha xy is the measure of a rectangle of width x and height y. So alpha 1 in particular is 1 because it's a probability measure. So actually it means that alpha xy is equal to xy, but then the limit measure must be actually the uniform measure, and if I have a uniform measure, then the probability, if I choose k points randomly independently of each other, I see every subpermutation with the density 1 over k factorial. So this is the proof that the property P5 implies pk for every k. So in order to prove the optimal result, we have to do a little bit more, and basically that more is on this slide. So this time we start with integrating according to the limit measure. So on the previous slide I was integrating according to the uniform measure, so this quantity was expressible using densities of 5 elements of permutations. So now I'm able to express it using 4 elements of permutation, and I apply Cauchy-Schwarz inequality. So I obtain this inequality, and now I will use a trick that will allow me. So this quantity is safe. So this quantity can be again expressed using 4 elements of permutation. So I just write here 1 over 9 for it. But this quantity is a little bit troublesome, but it can actually be shown that if I draw a careful picture, then this integral is equal to this. So this integral is equal to this. And I'm not going to provide you a proof, but it's basically kind of a double counting of mass, similar like if you have a bipartite graph and you know that the sum of degrees in one part is equal to the sum of degrees in the other part. So this is really just a trivial identity. In some sense you just have to draw a couple of right pictures to see it. But once you have this, then this can now be expressed using 4 element subpermutations, and this is the quantity we saw on the previous slide. So we know that this is at most some number, we can compute that number, and that number happens to be 1 over 81. So I know I must have equalities everywhere from the left hand side to the right hand side, and in particular one of the inequalities was the one we saw on the previous slide, so I get again the same conclusion as on the previous slide, and this completes the proof and also the first part of my talk. So maybe this might be a good time for questions. Okay, it doesn't seem to be the case. So the second part of my talk is more computer science oriented, and I wanted to make a joke that kind of corresponds to my appointment in Warwick, where I have a joint appointment between math and CS. So now I'm moving to the CS side, and I want to be talking about property testing. So I already mentioned at the beginning of my talk that the general idea of property testing is that we're able to conclude properties of large objects just from a small sample of it. And what kind of properties one can have in mind? So there's a big area of property testing in particular for graph properties. It has been shown that every hereditary graph property is testable. And one example of such property is testing whether the graph is triangle free, whether it contains a triangle. And for permutations, maybe we may think whether our permutation contains some fixed subpermutations, so maybe it contains 1, 2, 3, 4, 5 as a subpermutation, just an example. So when we say that a property is testable, we say that a property is testable if for every epsilon, for every positive epsilon, where x is an algorithm A and an integer k, such that if I present the algorithm A with a sample of my input object of size k, then if the input has property p, then the algorithm must accept with probability 1 minus epsilon, and if the input does not have the property p, but I need here that it doesn't have the property p in some strong sense, so I'm saying it must be epsilon far from having the property p, then the algorithm rejects with probability at least 1 over epsilon. So now that I need this epsilon far here, so for instance if I decide to test whether my graph is triangle free, then what I probably want to do is I take the sample. If I don't see a triangle in it, then I accept. If I do see a triangle in it, then I don't accept, but maybe my graph is huge and it has just one triangle somewhere. So it would be, with probability 0 I can see it, so I need my graph to be somehow far from being triangle free. So in the case of graphs, the distance is usually defined as the proportion of the edges you have to change that your graph will not or will gain the property. So the distance of two graphs is the minimum number of edges you have to alter to get from one graph to the other. And the distance from the property is the minimum proportion of edges you have to change that your graph will start having the property. So if your graph has just one triangle, you just remove one of the edges, but one of many edges, so basically you get to a graph that's considered to be very close to your input object. So with Terka we were looking at permutation property testing. So let me now restrict just to hereditary properties. So these are properties that if a permutation has that property, then any subpermutation has that property. So very close under taking subpermutations. And Hoppen, Kohayakawa, I do apologize for having a misprint on the slide, Kohayakawa, Moreira and Sampaio, they showed that hereditary properties of permutations are testable with respect to something which I call regular distance, and the distance of two permutations sigma and pi is defined. So there's some normalization when the distance is always between 0 and 1 is the maximum over all intervals s and t, where s and t are intervals of integers from 1 to n, of the number of points that sigma maps from s to t, and pi the difference of the number of points that sigma maps from s to t and pi maps from s to t. So maybe I draw a picture. So I choose an interval s and I choose an interval t, and I look how many points pi and sigma have in this rectangle. So I look at the relative distance of the number of points. And this is what they call regular distance, and it's actually related to the regularity lemma for permutation, and it's closely related. As you may see, it kind of resembles the pictures we saw in the theory of limits of permutation. So it's also related to the existence and the uniqueness of the limit object for convergent sequences of permutations. And they showed essentially using similar techniques that are known for testing graph properties and many other properties. They show that these hereditary properties of permutations are testable with respect to regular distance. And in particular, that tester is very special in the sense that it's presented with a sample. If the sample has property P, then it accepts, and if and otherwise it rejects. So in order that this tester works correctly, you need to know that if your permutation is epsilon far from property, then almost no sample would have this property. And this is the main result of their paper. And they asked whether hereditary properties of permutations can be tested for a different notion of distance between two permutations, which is namely Kendall-Tau distance. So now the Kendall-Tau distance is based on the number of pairs of elements I and j, that the ith element in one permutation is smaller than the jth element in the other, and is vice versa that the ith element is smaller than the jth element in the first permutation, and is vice versa in the other. So the number of transpositions among the pairs of elements. And actually this is also equal to the number of minimal transpositions you must do between consecutive elements to change one permutation to the other. So it's kind of an analog of the edit distance that I have mentioned for graphs. It's like kind of a natural way how if you want to modify one permutation to the other, you probably want to do it through transpositions of consecutive elements. So it's not hard to show that the regular distance I have mentioned on the previous slide is always smaller or equal, actually linearly bound to the Kendall-Tau distance, but the difference between the two distances can be arbitrarily large. So if you take two random permutations, and by random now I mean you really choose two random permutations, when in any big rectangle they will have similar densities. So the regular distance of two random permutations is essentially 0, but on the other hand the Kendall-Tau distance is 1/2, because if you fix I and j with probability 1/2, you will see different order in one permutation than the other. So the regular distance could be much smaller than the Kendall-Tau distance. And therefore, if you have a tester with respect to Kendall-Tau distance, you of course have a tester with respect to regular distance, because if you epsilon far in the Kendall in regular distance, you also epsilon far in Kendall-Tau distance, but the converse conclusion is not true. And with Terka we proved actually that there exist testers with respect to Kendall-Tau distance, and we prove it again that the trivial tester is the right one. So if you have a hereditary permutation property P, and you present it with a permutation which is epsilon far from this property in the Kendall-Tau distance, then almost no sample of size where the size depends on epsilon and property P has property P. So at this point I would probably not go into technical details of this result, but I will just mention that unlike many algorithms or many proofs of correctness of algorithm in this area, our proof is not based on any kind of regularity decompositions. Of course we somehow have to capture the structure of the permutation, but we're not using any regularity lemma tools or anything like that. So that might be important, maybe just from theoretical point of view, if one wants to look at the dependence of this k on epsilon and p, because like the constants appearing in the regularity lemma, they usually are Taylor functions in 1 over some polynomial in epsilon. So there's now a better proof for the removal lemma due to Jacob-Fox, where this dependence was heavily improved. And removal lemma is actually the tool we want to use for property testing. But having a proof that avoids the regularity machinery, and that's a direct proof, might be important. First still you're getting functions which are double functions or which are double exponential, which is actually the case of our proof in case that P is defined by forbidding some subpermutation. But the dependent is much better than if you use the regularity lemma. So I probably, do I still have 5 minutes or not? I may stop now or tell one more result.
5 minutes.
Okay, so I tell one more result. So with Terka we were also interested in something which is called parameter testing. So now the tester should not decide whether an object has some property, but it should approximate some parameter. So let's say a parameter will be a function which assigns every permutation a number between 0 and 1, and I will say that the parameter is testable if, when the tester is presented a sample of a constant size with probability 1 minus epsilon, it says the value of the parameter is this, and it differs by at most epsilon from the correct value. And in order to be testable, it's enough that the property is something which is called finitely approximable, which means that for every epsilon there exists some f and some function f, such that you may correctly say the density, you may correctly approximate the parameter p using this function f just based on densities of subpermutation of length m. So for every epsilon you will get a function to which if you tell the densities of subpermutation of order m, the function will tell you the value, and this value approximates the parameter you're interested in for sufficiently large permutations. So this notion is a little bit stronger than the notion of being finitely forcible, where here the order of permutations whose densities you're interested in may depend on epsilon. And this is good for testing, because when you have a big sample, from the big sample you may correctly approximate densities of subpermutations. Finitely forcible is stronger in the sense that the order from which you want to guess the parameter must be independent of epsilon. So we want that there exists a universal order and a universal function such that for every epsilon the property of the permutation is fully determined by the densities of these small subpermutations. So a question from a paper of Hoppen, Kohayakawa, Moreira and Sampaio, we were looking at permutation parameter testing, was where there exists a parameter that's finitely approximable but not finitely forcible. So clearly we are finitely forcible, you're finitely approximable, you're finitely approximable, you're testable, and we wanted to know whether there's a difference between being finitely approximable and finitely forcible. And the answer is yes. So we actually gave a constructive example, or semi-constructive. So this is a joint work with Roman Webov, who will be my postdoc in Warwick since January, my student Terka Klimošová, Hongliu, who's a student of Jiří Balog in Urbana-Champaign, and another graduate student, Honza Volec. And we gave a construction, and besides giving a construction for permutation, we also showed that the same is true for graphs. But this is not a new result, this already was known, and one of the proofs is somehow related to the existence of non-finitely forcible graphons. So actually almost every graphon is not finitely forcible, and I think I will not go into explaining what this expression means, and I will just say that the proof we gave is kind of more constructive. That like we almost get the graphs, or even better, or graphs or permutation where exists a finite algorithm that would construct the property, or that you actually compute the property P in some sense. And I think I will just end here, and thank you for your attention.
Thank you. Do you have any questions?